In this video, we're going to solve an example from Chapter 3. This example is going to be talking about logarithmic differentiation. Now remember, in this chapter, we first introduced the derivative, the main definition of the derivative, and how to find it, and then we introduced different kind of functions with their derivatives. Also, we gave you many rules that's going to help you in your calculations of derivatives for many types of function and expressions. Also, one of the expressions that we encounter in this chapter is that y is equal to variable raised to a power where we are going to have a constant. One example of this one is that y is equal to x to the power pi. Now, if you wanted to find the derivative of this function, then dy over dx is equal to pi times x to the power pi minus 1, where we used power rule here. Also, we have another expression that we encounter in this chapter, where we are saying that y is equal to a constant raised to a power where the power here is going to be a variable. Such an expression for this one, we call it exponential function. An example of this one is going to be y is equal to 3 to the power x, and the derivative of an exponential function is going to be 3 to the power x times ln of 3. But we might also have another expression that is having y is equal to variable raised to another variable. So both the base and the exponent, we have both of them are variables. In such an expression like this one, how we are going to deal with it if we wanted to find the derivative dy over dx? Are we going to consider it as in type 1 type of an expressions, and we are going to use the derivative using the power rule? Or are we going to consider it like the form of the second term as an exponential functions and find the derivative as an exponential function? Well, in this case, neither. In order to find the derivative here, we need to use something which is called logarithmic differentiation. An example that's involved logarithmic differentiation is the following question. Let y is equal to ln of the absolute value of x raised to a power x. The question is asking you to find dy over dx. This form of the expression is like our third type. So we need to use here logarithmic differentiation in order to find the derivative. Okay, let's see how we are going to solve this problem and how we are going to treat it. The problem here is that occurring in the variable in the exponent, we wanted to somehow to bring it down. So how are we going to do that? Well, we are going to use some of the laws of the logarithms. So y is equal to ln of the absolute value of x to the power x. Now, the first step is that we need to take x down. So how? By taking ln for both sides of your equation. So ln of y is equivalent to ln of the absolute value of x to the power x. So using the properties or the laws of the logarithm, then we could take x down. So it's going to be x times ln of the absolute value of x. Now, in order for this function to be defined, the outer ln of x, then we need the absolute value of x to be greater than 1. Because if this is the case, then that will guarantees for us that ln of the absolute value of x is going to be a positive quantity. Which means that the outer ln is going to be defined because, as you know, ln function is only defined for positive number. Okay, to make this concept clearer for you, let us graph the function ln of the absolute value of x. Remember, ln of the absolute value of x, you could write it as a piecewise functions whenever x is greater than 0 or less than 0. The graph is going to look as follows. When x is greater than 0, then this is going to be like ln of x, like the graph of ln of x. When x is going to be less than 0, then the graph is going to look like ln of minus of x. So it's going to be a reflection about the y-axis. So the graph y is equal to ln of the absolute value of x is going to look as the following. Now from the graph, you notice that if your x between -1 and 1, then this piece of the graph is going to be below the x-axis, so it's going to have a negative value. So that means in your expression, the outer ln is not going to be defined for a negative number. So it can't be defined, this function, or ln of the absolute value of x is not going to be defined. But if the absolute value of x is greater than 1, which means x is greater than 1 or x is going to be less than -1, then that means you could see from the graph that the graph is going to be above the x-axis, so it's going to be a positive quantity. Ln of the absolute value of x is going to be a positive quantity. Now this is really important for us. Once we clarify this one, then let's go back to the main question, which is finding the derivative. Well, differentiating the left-hand side of your expressions, we are going to deal with y as a function of x, so we are going to differentiate it implicitly. So it's going to be 1 over y times dy over dx. Now the right-hand side is a product of two functions, so we are going to use the product rule here. We are going to take the derivative of the first term, d over dx for x, times ln of the absolute value of x, plus the first term x times the derivative of the second function, ln of the absolute value of x. Now, in the second term, remember that we have a composition of more than one function, so we need to use the chain rule for the derivative. So we could rewrite the derivative of x as 1 times ln of the absolute value of x, plus x times the derivative of ln of the absolute value of x, as the derivative of the outer function ln, which is equivalent to 1 over ln of the absolute value of x, times the derivative of the inner function ln of the absolute value of x, which is 1 over x. This one is going to be equivalent to 1 over y times dy over dx is equivalent to ln of absolute value of x plus 1 over ln of the absolute value of x. Notice that we have x's here, which is going to cancel off each other from the first step. Multiply both sides by y, so dy over dx is equal to y times ln of the absolute value of x plus 1 over ln of the absolute value of x. Remember, your derivative have to be in terms of x, so you need to substitute back the value of y, which is given in the heading. Y is equal to ln of the absolute value of x to the power x. And this is going to give you the desired derivative, dy over dx. This function is defined whenever the absolute value of x is going to be greater than 1. I hope this example was a good illustration for logarithmic differentiations, and will give you an insight how to use it in order to solve expression that's having the form y is equivalent to variable raised to another variable.